Welcome to RLD Academy. In this video, we will discuss about bipolar junction transistor. In particular, we will discuss about operating regions of BJTs. From this video, you will get the followings: what is BJT, how it works, and what are the applications of BJTs. We will discuss three operating regions of BJTs: active region, cutoff region, and saturation region. And we'll discuss how to check the active and saturation region of BJT if circuit is provided. Also, we'll discuss which parameter IC or VCE is getting saturated, or both the parameters are getting saturated in saturation region. And at the end, we'll solve one problem. This is the problem we'll solve. It appeared in GATE ECE 2014. This video is going to be a little bit lengthy, but if you can go through it till the end, I am sure that you will get clear concept about BJT. Let us start. This figure shows the pictures of real transistors. You may notice that BJT is a three-terminal semiconductor device. We'll have two types of transistors. One is NPN transistor, another one is PNP transistor. We'll use particular symbol to represent these two transistors separately. We'll consider this symbol for NPN transistor. It is having three terminals. One is called base, this one. This is our collector. This one is emitter. Now we can notice that there is an arrow between base and emitter. From base to emitter, the arrow is provided. It indicates the direction of current flow. So if current is flowing in the transistors, then from this to this one, current is flowing. Okay, meaning is that the emitter current is downward, this side, right? Now we'll use this one, this figure, to represent the construction level of NPN transistors in a single semiconductor, but we can make these three regions. One is N type, next one is P type, another one is again N type. We'll discuss these things in detail later. So middle one is called base, and one side is emitter and the other one is collector. But we'll discuss in detail later about this one. Now in contrast to NPN transistors, in PNP transistors, the symbol is this one. It is similar, only difference is this one. The arrow is provided from emitter to base. Again, it indicates the current flow. As it is a PNP, from P to N, current can flow in semiconductor device, okay, in diode. That's how this arrow is provided. This is your P type, this is your N type, this is your again P type. Okay. Now we'll focus on NPN transistor. And we get two major applications for transistors. One is electronic switch, other one is amplifier. So we can use BJT as an electronic switch elements, or it can be used for amplification purpose. We can design voltage amplifier, we can design current amplifier, even we can design other amplifiers like trans impedance or trans conductance amplifiers. Okay. But in this video, we will focus on biasing circuit. Means we will add extra circuit elements using resistors and voltage sources with these transistors so that it will be applicable for certain applications. Okay, we'll make it suitable for certain applications. Either it will be used for switching purpose or it could be used for amplification purpose. So for that, we need to add some certain circuit with these transistors. So first, within base and emitter, we'll provide one voltage source here and one resistance. right? And this end is plus terminal, and this is your negative terminal for NPN transistors, right? Now this arrangement, this p type here, because NPN, p is connected to positive, n is connected to negative, then this diode will be forward biased. So we'll discuss in detail little bit later. So this is the arrangement in base side. This voltage source is called VBB. This resistance, the current limiting resistance, is RB. Similarly, on this side, collector and emitter side, will connect one source and one resistance. This is called VCC, and resistance symbol will use R sub C, right? Now we'll define the regions, three different operating regions of BJTs. Okay. So first one is cutoff region. What is cutoff region? To understand cutoff region, we need to understand these junctions. JBE means junctions between base and emitter. This junction, and again one more junction between base and collector. This junction between base and collector, there is a junction that I'll call it JVC, and we'll try to get the relation in each operating region, and also we'll find the applications of that region. Okay, now I'll discuss briefly about this diode, PN diode, when it will become forward biased and when it will become reverse biased. So if this P type semiconductor, P side, is connected to positive terminal and N type is connected to N type semiconductor, then this circuit will conduct and will get a current flow from P to N. Okay, so this side as it is shown, and this arrangement is called forward biased, right? So in forward biased circuit, diode will conduct and will get certain current, and current will flow from P to N, right? Whereas in the reverse biased, you will see this N type semiconductor is connected to plus terminal, battery source, voltage source, and P type semiconductor is connected to minus terminal, negative terminal. So in this arrangement, there will be no current flow. Current cannot conduct. So in reverse bias, diode cannot conduct, current will become zero. Very simple information that we'll be using here. Though we'll discuss the operations of diode in detail in some video. Okay. Now in cutoff region, both the junctions, this PN diode, this is on P type, this is on N type. So we can consider this is one diode, PN diode like this. Similarly, this P and this N, another PN diode here, and this is the junction between base and collector. And both the diodes, mean this junction JBE and JVC, if both are reverse biased, then no one will conduct. So you can expect that the current to the base, that is IB, current to the emitter IE, or current to the collector IC, all will become zero. No current will flow in the circuit. So this situation is used for switch off application. So we can consider that circuit is switched off. Nothing is working. Okay, we don't get any current in the circuit. So that is equivalent to switch off. So this is arrangement, right? Next one is forward active region. In this region, junction base emitter is forward biased and junction base collector is reverse biased. This base emitter junction is forward biased, and we need to make base collector reverse biased, then only it will be called as forward active region. And in this region, you will get this equation, IC equals to beta IB. It says that the base current is independent. Okay, we can get the current IB depending on this voltage source and resistances. Okay, but the IC is controlled by base current, and it is beta times some constant times IB. So this is a linear equation, IC equals to beta into IB, and this is used in amplifier. We can design voltage amplifier, we can design current amplifier, but the transistor should be in active region, then only we can design such amplifiers. Next is saturation region. In this region, both the junctions, junction base emitter and junction base collector, they are reverse biased, and under this condition we'll get that VCE is becoming 0.2 volt. This is almost constant, and we can use this relation for switch on purpose. So for switch off and switch on, we can use cutoff and saturation region respectively. So these two regions are used for electronic switch purpose applications, and forward active region is used for amplifier. We have one more operating region. It is called reverse active region. This is just opposite to forward active region. Here also one junction is forward biased, another junction is reverse biased. In this case, base collector junction is forward biased and base emitter junction is reverse biased. However, this reverse active region is rarely used. I'll show you its application while we'll design TTL NAND gate. Okay, totem pole TTL NAND gate, there this reverse active region you can find out. Okay, now we'll skip this part. Now we'll focus on NPN transistor in more detail way to understand these operating regions. First, we'll consider the construction level of NPN transistors, the physical structure of NPN transistor, the width for these three regions, this for collector, base, and emitter. And you understand the emitter, the name. Emitter means it should emit the carriers. In NPN transistor, the majority carrier for this N-type semiconductor is electron. So from this region, these electrons, free electrons, will be emitted towards the base, and it will try to cross this base barrier, and then it will enter the collector region, and there those electrons should be collected. That's how it is a collector. And from here electrons will be emitted. That's how it is a emitter, and this is a via or base part. Okay, we can control this operation. We can have certain control on this operation using this base terminal. Okay, now based on these applications, we'll design these NPN transistors as the more number of electrons should be here, and its purpose is just to emit the electrons, right? And but here the collector, you need to collect all the electrons, so maximum times we will get the more dissipation power in the collector. Okay, that's how the width or the cross-sectional area of this collector side should be more. So if the width is WC here, and width for base is WB, and width for emitter is WE, then WC is having the largest value. Okay, and whereas this base is having the lowest width. It should be very narrow one, because electrons should cross this barrier, these regions, and it should enter to the collector side. So that's how it is maintained very narrow. So WB should be very small compared to WE, and WC should be largest one, so that it can collect all the electrons efficiently and it can dissipate power easily. Okay, next, the doping concentration level. Now here we'll make N-type, this is P-type, this is N-type, but this region is used for emitter, means here we should have a huge number of free electrons. Thus doping concentration level for this region should be the highest one. Okay, and this region, the collector region, its purpose is just to collect the electrons, those electrons which are coming from emitter towards this collector through this base. Okay, thus in the collector the concentration level is the lowest one, and the concentration level in the emitter side is the highest one, and base it could be in the middle. Okay, thus n sub E will call this concentration level, doping concentration level. You know that to make n type we have to use pentavalent impurity. We have to add this one pentavalent impurity, then only on the semiconductor we will get n type. And to make is p type, we have to add trivalent element, then only we'll get p type semiconductor. Okay, but the doping concentration means this impurity, number of impurity will add, that should be very large for this emitter side compared to collector and base, right? Now we'll discuss a little bit about forward biased diode in detail for practical forward bias. Earlier we have said that already. This forward biased diode, the p type should be connected to plus terminal and n type should be connected to negative terminal. But in reality, for practical diode like silicon diode, we'll get sufficient ID current if the potential drop across this diode is about 0.7 volt. So Vd equals to 0.7 volt, we can consider. That time only we'll get sufficient current ID from P to N side. Okay, so that amount of voltage you need to add here. Then only you will get sufficient current here. But if Vd is 0.5 only, then ID starts flowing. That's the important thing. So this silicon diode will start conducting if the potential difference between P to N is about 0.5 volt. Okay, but you see that in ideal cases, I have said if this plus terminal is connected to plus this p type, then only it will conduct. But for practical diode silicon, it will not conduct. So if you consider suppose 0.4 volt here, if you apply, this diode will not conduct, right? So you need to have at least more than 0.5 volt. So if this potential gap is 0.5 volt, then only diode will conduct. Okay, and you will get sufficient current if the potential gap here is 0.7 volt, right? Now we'll focus on this transistor biasing circuit. Already I have said that in base and emitter we'll add this source VBB and base resistance RB, and collector side we'll consider VCC and resistance RC, right? And this node potential we'll consider VE, and it is connected to earth, actual grounded, that VE equal to 0 volt. With respect to this one, this potential is VB and this potential is VC, right? And here also we'll draw this circuit to understand the operations on BJT in more detailed way. Now we'll consider the voltage gap between these two junctions, base and emitter. This voltage gap I'll call it base emitter voltage V sub BE, and between collector emitter this voltage difference I'll call it VCE. VBE and it is VCE, right? For cutoff region, as we mentioned that in cutoff region both the junction base collector and base emitter should be reverse biased. So this arrangement, you see, this is your NPN transistor. N type is already connected to plus terminal. Okay, so if this is true, then we can expect that this PN diode between base and collector, it is reverse biased. But it is not always true. Okay, for time being, assume that it is reverse biased. And this PN diode, base and emitter, if we consider this way, this is plus, this is minus, P is connected to positive, then it will become forward biased. So to get cutoff, this potential VVV, as I said that it should be very low, close to 0 or negative, then this PN diode will be reverse biased. Because this transistor is made of silicon semiconductor, thus we can see that this potential is very low, around 0 volt or less than 0.5 volt, then this junction PN diode will be reverse biased. Okay, and if VCC is high, around 10 volt, then this base to collector junction is again reverse biased. Thus both the junctions are reverse biased, means it is in cutoff region. So this is the condition. This potential, this source should have 0 volt or negative voltage, and this potential is positive potential, and we will get cutoff region. Okay, in cutoff region, you understand there is no current flow. All the current IB, IC, IE, they are negligibly small. Now we'll consider active or saturation region, active and saturation region, both simultaneously. Now for that, so this VVV should be at least more than 0.7 volt, and VCC is also sufficiently large, right? This circuit will be used for both active and saturation region. Now depending on the values for resistance RB and RC, we will get these two regions, active and saturation region. We need to understand this thing clearly. Okay, so same circuit could be in active region or it could be in saturation region, depending on the values for VVV, VCC and RB, RC, and also the current gain factor beta. The IC by IB equals to beta, that you know, that ratio is called current gain in active region. Okay, let us understand this thing clearly. Now here we will assume that this VVV is around 5 volt and VCC is suppose 10 volt, right? Now consider the base side. In base side, this side, base side is independent side. It does not depend on collector side. Okay, so independently we can calculate all the voltage and current in the base side, means VB we can calculate, IB also we can calculate independently, right? Now here IB will be this current IB, obviously this is your source. If this potential gap is VBE, this end is zero potential, so VB is nothing but VBE. So the current flow here IB will be this potential VBB minus this potential VB upon the resistance RB. That one, okay. And if I assume that VBB is around 5 volt, then base emitter junction is forward biased, and once this base emitter junction is forward biased, the VB is around 0.7 volt. It is constant. We'll consider VBE is around 0.7 volt for forward biased junction, right? Now we can consider the collector side, this side. In collector side, we need to understand about collector base junction, whether it is forward biased or reverse biased. You know that if this is reverse bias, base collector is reverse biased, then it will be in active region. But if base collector is forward biased again, then it will be in saturation region. Now how to understand these things, whether this region is forward biased or reverse biased? Okay, that's the main important concept here. Now to understand these things, first we will try to calculate the VC, the potential at this point, because we need to find out the gap between VB and VC, okay, right? So what is VC? VC is here. So this is the source, 10 volt source. The current is flowing this side, IC current we have assumed. So whenever current is flowing downward, the current to the RC is IC, So you will find one voltage drop across the resistance RC. That voltage drop will be IC times RC. So supply voltage is 10 volt. It will supply, and there is a drop across RC is IC times RC. So rest will be available at this collector end. So collector potential Vc will be Vcc minus the drop across the resistance RC, IC into RC. That is available at this end. Okay, that is very simple. Now, this potential Vc, it depends on these two factors. One is IC, actual value of IC, and RC as well, right? If I know the Vc, then we can calculate the gap between Vb and Vc. So Vc is actually Vb minus Vc, the potential at base node and potential across the collector node. This gap is Vbc. Okay, and we have already said that this junction, base collector junction, will be forward biased or reverse biased depending on this potential gap. So this gap, if it is more than 0.5 volt, VBC, if it is more than 0.5 volt, then only it is forward biased. Otherwise, it is reverse biased. Be careful here. I have said that in semiconductor diode, the diode will start conducting if it receives more than 0.5 volt. Then only it will be forward biased and it will start conducting. And if it is getting 0.7 volt, it will conduct finally, and the current is sufficiently large, right? Now first we will assume that this VC is more than VB, because VB is around 0.7 volt, because this circuit is independent, I have said, and this VE is 0 volt. Potential gap between base and emitter is 0.7 volt, that I have mentioned. So this base potential is 0.7 volt. So this is known to us. Okay, we have used 5 volt here. We have used RB certain such values for RB. Then we'll get this base potential 0.7 volt. Now we'll assume that VC is sufficiently large because this is 10 volt applied. So I can understand that this potential is around 10 volt or a little bit less. It's fine, but it is much larger than 0.7 volt. So as VC is more than VB, so VC is negative, and negative means obviously reverse biased. So this junction, base collector junction, is reverse biased, base emitter junction is forward biased, thus it is in active region. So we'll start with this assumption, right? Now we'll understand this thing here, and we know that this n type in this emitter side here will get free electrons. It is highly doped region, n type, thus we will have huge number of free electrons. And whenever this base emitter side is forward biased, then these free electrons are moving towards the base. Okay, because this diode will contact, this PN diode will contact, these electrons will move towards the p-type semiconductors, and from the these holes of the p-type semiconductor, we can assume that it is moving towards this side, emitter side, right? So here we will consider this thing only, the reluctance only. Electrons are moving from N to P, right? So whenever these electrons are moving towards this collector through this base region, in the base you will find few holes, okay, because this base region is made of p-type semiconductor, it is having positive holes. So those holes can decombine with these electrons, negative charge carrier electrons, they can decombine, okay, but this region is very narrow, okay, thus most of the electron will cross this barrier and will enter this collector region, and once it is entering to the collector region, due to this positive terminal, those electrons are attracted toward this plus terminal and it will be collected here. Okay, so from here electrons are generated, emitted, and here those few electrons are collected here. Very few electrons are getting recombined with the holes. Okay, so here we'll assume that, suppose if we assume that only 2% is there's a recombination rate. Okay, we will recombine with the holes, and rest 98% of electrons are entering to this collected region, right? So the collector current is due to these electrons, and the base current is due to this recombination, and emitter current is due to the movement of these free electrons, right? So here we can find the current, base current, collector current, emitter current accordingly. So this is a base current, this is the collector current and emitter current. You can see here that this is the movement of electrons. Electrons are moving from emitter towards the n-type semiconductor collector side. Then it is collected by this source point terminals. Okay, as electrons are moving in this side, the current to the collector will be the opposite of the flow of electrons. This is the current flow IC, and this is the current flow IB, and this is the current flow to the emitter. Okay, so this IB plus IC will give you the total emitter current. Now here this IC upon IE, this ratio. So out of 100% electrons, whatever it is generated here, emitted from this emitter side, only 98% are coming to the collector side. So the ratio IC and IE will be 98 upon 100, means 0.98 for this example. So this ratio is called alpha, right? Similarly, we can define the ratio between base current and collector current. So IC upon IV, we can see that 98% electrons of total electrons will give you the collector current, and 2% only give you the base current. So the ratio IC and IV in this example will be 98 upon 2. Okay, means 49. So this quantity is also fixed for active region, and this ratio is called beta, the DC current gain between collector and base, right? Now we'll try to understand this thing in detailed way, when you will get active region and when you will get saturation region, because I have said that same circuit, this circuit could be used for active or saturation region. We have assumed that it is in active region, but it is not always true. Okay, now we'll try to explore more. Now we'll vary this RV resistance. Suppose VVB is given, VCC is given, RC is given, beta is also mentioned for these transistors. Now we'll vary RV. If RV is reduced, then what will happen? Now already I have said that this base side is independent. In transistor, the base side is always independent if there is no feedback, right? So in this case it is independent because this potential gap is VBE. So this current IB is simply, I have said, VVB minus VBE upon RB. So as RB is reduced, so this part is reduced, so obviously IB will increase. So effect of this one, whenever we reduce RB, we'll get more base current, right? And if we get more base current in forward active region, this IC by IB is beta, IC equal to beta times IB, so obviously IC will also increase. Okay, so this ratio is maintained. IC by IB is this ratio is maintained in active region. So as IB is increasing, IC is also increasing. Okay, so its meaning is that more number of electrons are emitted As more number of electrons are emitted, the ratio will remain same. 2% is recombined and 98% of electrons will flow. But as more number of electrons are moving, that's how the emitter current is more. But ratio is maintained. Okay, thus IC versus IB, the IC upon IB is again 49. This beta is constant. Okay, but if IB is more decomposition you will get as more number of electrons are coming. IB is more. Simultaneously, more number of electrons are moving here as well. IC is also more. So IB more means IC is also more. Beta times of IB. Thus, IC is also increasing, right? And as IC is increasing, what is happening? In VC, the potential across this point. The potential is VCC minus IC into RC. As IC is increasing, so this part is more drop you will get across RC. So available voltage across the collector terminal is less, is reduced. So we can understand that BC will reduce, right? Now we'll start with one value. Suppose for certain values for RB, this potential, collector potential, is 9 volt, right? Suppose RB equal to 1 kilo ohm. For this RB equal to 1 kilo ohm, we are getting suppose 9 volt here. This is your 10 volt. 1 volt is drop across the collector region, collector resistance. So only 9 volt is available here. It is fine. Now, if we reduce this resistance little bit, we'll get more collector current. So it will reduce this potential VC that we have explained. Okay, so VC will be reduced. So what we can expect? Okay, suppose it is reduced to 5 volt. Now, if it is 5 volt, now we want to understand whether this junction, base collector junction, is reverse biased or not. Now you see the base potential is VB is 0.7 volt and VC is 5 volt. So VC is still larger than VB. VC is more. It is 5 volt. VB is only 0.7 volt. So this is negative. VBC is negative. Means the base collector junction is reverse biased. Because this is P type, this is N type. P type should be connected to more positive and N type should be connected to negative terminal. Then only it is forward biased. So as VC is more than VB, obviously this junction, base collector junction, is reverse biased. So still it is in active region. It's still reverse biased. Now further, if you reduce this resistance, what will happen? We will go on reducing the resistance. Then again you will get some reduction in collector potential BC. Suppose it is now 1 volt, reduced to 1 volt. Still it is in a active region because this is 0.7 and this is more, 1 volt. Right? So this gap is negative. It is reverse biased. Now if it is reduced to 0.7 volt, then what is happening? This is 0.7, this is again 0.7. So what is the gap? The gap is 0 volt. Is it forward biased? If it is ideal diode, then obviously it is forward biased. But for practical silicon diode, I have said that diode will conduct if and only if the PN diode is having more than 0.5 volt. That I have said already. So if gap is only 0 volt, diode is not forward biased. Silicon diode is not forward biased. So this silicon diode will start conducting if and only if it will get this potential gap around 0.5 volt. Okay, so this P type should be having more potential by 0.5 volt compared to N type, N side. Right, now the gap is same, it's 0 only. Right, now suppose it is reduced to 0.5. Now it is more, 0.7. This is 0.5. But how much gap it is? 0.7 minus 0.5 is only 0.2. So 0.2 is not sufficient to make it on. So that will not conduct. It is not forward biased. So as this junction is not forward biased, still it is in active region. Now, if it is reduced to 0.2 volt, now you see the gap 0.7 minus 0.2 equals to 0.5 volt. This time, this junction diode, PN diode, will start conducting, means it is now forward biased. And once it is forward biased, that region will be considered as saturation region. So thus, in saturation region, the potential here, Vc, should be 0.2 volt or less. So if it is 0.2 volt or less, then obviously this junction will be forward biased, and we can make conclusion that this transistor will be in saturation region, because this is forward biased, this is again forward biased, so transistor is in saturation region, right? So now we'll conclude this thing, that in saturation region, the VCE, this collector to emitter, this potential is about 0.2 volt. It is not reduced greatly below this 0.2 volt, because that time it is forward biased, and this collector side is again, it becomes independent. Okay, earlier in active region it was dependent on the base side, because IC was beta times of IB, and this time this collector current is almost independent of IB. Okay, so that current we can calculate. So BCE, this potential is almost constant around 0.2 volt in saturation region, and we can calculate that time the current in saturation region. Current will be then BCC minus VC, because this is the voltage gap across the RC. This potential is VCC, this potential is VC, so this VCC minus this potential is 0.2 upon RC will give you this current IC. So IC under saturation region will be VCC minus 0.2 upon RC. And you can see this current is independent of IV. It is here that IC equals to beta IB is no longer true. Be careful. Rather, IC is less than beta times IB. Okay. In active region, whatever current was there in IB, the IC was proportionate, beta times IB. But in this case, what is happening? Suppose here huge number of electrons are coming here. So 2% recombination is fine. Because of that, IB current is you are getting. So huge number of electrons also coming, but the collector side cannot collect all the electrons. So there will be certain storage of electrons here. Okay, so it has certain capacity. So it will be collecting few electrons only, maximum currents. So that current will be this current. So this current is saturated, IC minus 0.2 upon RC. It cannot get more than that current, though the IB current is increasing, right? Okay. So if we want to draw the IB current versus IC current, because here we assume that RB is reduced continuously. As RB is reducing, IB is increasing. We want to see what is happening in IC. I have said that IC equals to beta times IB for active region. So in active region, already I have said that IC equals to beta IB. And in active region, we need to make sure that base collector junction should be reverse biased. And it will be reverse biased if and only if this potential VCE is more than 0.2 volt. Thus, VCE, if VCE is more than 0.2 volt, then base collector junction is reverse biased. It is maintained. And already I have said that this base emitter junction is forward biased. And again, base collector is reverse biased. Thus, it is in active region. Okay. So in active region, we have these two information. One is IC equals to beta IB. And other one is VCE is more than 0.2 volt. One inequality, one equality sign. Similarly, in saturation, one equality, that VCE saturation is 0.2 volt and IC should be less than beta times IB. Okay, and the saturated value will be VCC minus 0.2 upon RC. Now, if we want to draw these things, so this IC saturation, we can find out this is one level. If all the values are given, RC is given, VCC is given, then under saturation region, this IC current will be this much, suppose. Now for active region, IC equals to beta IB. It's a linear equation. Okay. So this one, IC equals to beta IB, one slope. Okay. Beta should be given. Generally, beta is very high, around 100. So this is the slope. But remember, this equation is only for active region. And in saturation, we can have only this much current, not more than that. So what will happen? I can consider that as RB is reducing, the IB is increasing. As a result, collector current is also increasing. But when it will try to cross this IC saturation, that time current will not increase further. It will be saturated here only. Okay. So I can say that this region up to this one, this is your active region or the linear region. It is also called linear region. And this side, this region is called saturation region. In saturation region, both the junctions are forward biased. In the active region or linear region, base emitter junction is forward biased and base collector junction is reverse biased. But there, that time, we'll get one linear equations, I is equal to beta IB. But in saturation region, this is not true. You'll get only maximum current IC sat, that is equals to VCC minus 0.2 upon RC, right? So this is the one figure. I hope you have seen this figure first time. You have not seen this kind of figure in any book or anywhere. Okay, so you want to explain another figure that you have noticed in the books or in some videos. Okay, that is IC versus VCE. Commonly we'll use this plot, this VCE versus IC, keeping IB constant. Now if we keep IB constant, then for active region you will get IC equals to beta times IB. So obviously that level is also constant. Now we'll consider one VCE saturation value. VCE sat is 0.2 volt. Already I said. So VCE is getting saturated at 0.2 volt here. So if VCE is more than 0.2 volt, this region is your active region and this region is your saturation region. So we can have one partition here, okay, based on VCE, not on IC. So in this curve, we can consider one partition with respect to VCE. Okay, if VCE is more than 0.2 volt, then only both the junctions will become forward biased. We'll get this region, this is the active region, and there the relation is IC equal to beta IB. But in this region, when VCE is less than 0.2 volt, both the junctions will be forward biased. Okay, then it will be saturation region, right? So there the IC is not equal to beta IB, rather IC is less than beta IB. Please remember these things. Now I'll draw these things. For a particular IB, suppose IB equal to 10 microampere, and if I consider suppose beta equal to 100, so IC equals to beta into IB, so 100 into 10 microampere means 1000 microampere means 1 milliampere. So IC equals to 1 milliampere for any voltage level, VCE. Okay, so if VCE is anything, if IB is constant, then IC is also constant. Okay, and that kind of situation you can get for different values of RC. Okay, Now, in saturation region, so I've already said it is almost constant here, but actually you can get this kind of slope, but this is very high slope. So forget about this part. I have already said if Vc is less than 0.2 volt, it is in saturation region, right? But ideally, practically, I can say that Vc is getting saturated at 0.2 volt only. Okay. For other base current, suppose IB equal to 5 microampere, current will be 0.5 milliampere. So this is the level. Okay. So it will be straight line up to this one, flat, this one, and here you will get on slope. But don't be confused. Here it looks like a linear, but it is not a linear region. It is a saturation region. Rather, this is called linear region or active region. So linear or active region, I think this figure is better because this active region, here you will get linear relation between IB and IC. That's how it is called linear. So you won't get linear relation between IC and VCE. Okay, in active region. Whether IC is flat, independent of VCE. Okay, in active region. So don't be confused. That's how I have drawn this figure. So this active region is again, it is called linear region because IC equals to beta IB, that relation is linear. And in saturation, IC is getting saturated. So this figure is more appropriate, more relevant, right? So for different IB, I can get this kind of this one, okay? Now how to identify the active and saturation region from that circuit? I've said that the same circuit is used for active and saturation region. Now, how quickly we can identify active and saturation region? So, what is the procedure? So, as I've said that base and emitter side, this side is independent for this figure from this other part. Thus, I can calculate first IB current. So, this IB current equals to VBB minus VBE upon RB. And already I said that VB is large, thus VBE, this junction is forward biased. Now once it is forward biased, this potential we can assume that it is 0.7 volt. So we can replace this by 0.7 volt if nothing is given. So I can calculate IB, right? Then we'll assume one region. First, we can assume that it is in active region. So if it is in active region, then we can use IC equal to beta IB. So with the help of this equation, we can find VCE now. So VCE will be, this potential across C is nothing but the VCC minus potential drop across RC. VCC minus IC into RC. That is the potential across collector to emitter. Okay. Now we have to make sure that whether it is really active region or not. It will be in active region if and only if this base collector junction is reverse biased. But if it is forward biased, then it will be in saturation region. So how to check this one? Based on this collector emitter potential. If collector emitter potential is more than 0.2 volt, I have discussed earlier that if VC is more than 0.2 volt, then only this junction is reverse biased. Okay. So check these things. If VC is more than 0.2 volt, then our assumption is correct. Means already I assume that it is active region, it will remain in active region because base collector junction is reverse biased. But if it is not true, it's less than 0.2 volt. After calculation, if you get these things, if it is less than some negative, then your assumption is wrong. Whatever you assume that it is in active region, it is no longer true. So if your assumption is wrong, means if it is in saturation region, then you need to recalculate the IC current because IC current is no longer true. It is not true. So IC will be now VCC minus 0.2 upon RC. Okay, be careful. So we'll start with this assumption, active region. We'll use IC equal to beta IB. We'll calculate VCE. We'll check VCE. If VCE is more than 0.2, assumption is correct, means it is active region, everything is fine. But if VCE is less than 0.2, some negative values, then obviously it is in saturation region. But whatever you will receive, this thing, VCE is negative. Suppose VCE is becoming minus 10 volt. It is not true, because VCE cannot be minus 10 volt. VCE will saturate at 0.2 volt only. Okay, thus the current will be different. Current will be VCC, and we'll assume that VCE is saturated at 0.2, then VCC minus 0.2 upon RC is the actual current in saturation region. Okay, so similarly we can use different things. We can start with this assumption that it is in saturation region. So in saturation region we can calculate the current IC considering VCC minus 0.2 upon RC. Then we'll check these things, IC upon IB. If IC upon IB is less than beta, okay, that means it is a correct assumption, because I have said that IC is less than beta IB in saturation region. Okay, but if you find IC is more than beta IB, that means that is wrong assumption. Again, it is also not true. IC wrong assumption means it should be in active region. In active region, IC equals to actually beta IB. So you need to recalculate these things. IC again. This IC is not true. So IC should be equals to beta times IB, and accordingly you need to calculate again VCE. VCE will be VCC minus this IC into RC. Okay, fine. Now we'll solve this problem. I hope you can solve this problem very easily. So this is circuit. 5 volt is connected here. 10 volt is connected here. This is your base resistance 50 kilo ohm. This is your resistance RC, and RC, different RCs are given. Okay, sometimes 1 kilo ohm, 3 kilo ohm, sometimes it is 20 kilo ohm. Okay, now we need to find out whether it will be in active region or saturation region or cutoff region. Now first thing, this is 5 volt, means base emitter junction is forward biased. This is NPN transistor, obviously it is forward biased, so it cannot be in cutoff region, right? This is ruled out. For any resistance RC, it cannot be in cutoff region because base emitter junction is forward biased. Now depending on this base collector junction, if it is forward biased, it is saturation region. If base collector is reverse biased, it is active region, right? Now what is the first step? First step is to find out the base current, because base current is independent. So base current is VBB minus VBE by upon RB. So VBB is given by 5, and VBE will assume that it's also mentioned that 0.7 volt, and RB is 50. Thus we'll get this 4.3 upon 50 milliampere. That means 86 microampere. Okay, fine. Now we'll assume that this transistor is in active region. Okay, so if it is in active region, what is IC? IC equals to beta into IB. This relation is true. Okay, so this is beta is given 50. So beta is 50 and IB is this one for 4.3 upon 50 milliampere. Okay, so total current will be 50 cancel out. It is 4.3 milliampere. So if it is in active region, then collector current will be 4.3 milliampere. We are sure, right? Now different values for R are given. Okay, now we need to check VCE. Then we'll decide whether our assumption is correct or wrong, right? So what is the VCE? VCE is VCC minus IC into RC. Okay, so here VCC is 10, IC we have obtained 4.3, so 4.3 milliampere, and we'll consider RC in kilo ohm. Then this milli and kilo they will cancel. I'll consider 10 minus 4.3 into RC only. Okay, now we'll choose those values. If I consider these three values RC, 1 kilo ohm, 3 kilo ohm and 20 kilo ohm, we'll find corresponding VC. Then we'll decide. Now for 1 kilo ohm, this is 10 minus 4.3 into 1. That means 4 minus 4.3 is 5.7 volt, which is more than 0.2 volt. So if it is more than 0.2 volt, what I've said, the base collector junction will be reverse biased. Means it will be in active region. Our assumption is correct. Okay, so this potential is more than 0.2, then only it is in active region. So it is not true. So this is in active region, right? So as it is in active region, but it is given that first choice 1 kilo ohm BJT operates in saturation region, it's not true. Okay, it should be in active region with this RC equal to 1 kilo ohm. Next, when it is 3 kilo ohm, it is 3, then 10 minus 4.3 into 3, it will give you minus 2.9, which is less than 0.2. So it is less than this thing. As an assumption is wrong, because it's if it is more than 0.2, then only it is correct. Okay, so as assumption is wrong means it is in saturation region. So with this 3 kilo ohm, the BJT operates in saturation region. Yes, it's correct. Okay, now we'll check last one as well. This 20 kilo ohm, again VC will become negative, minus 76 is more negative. Okay, minus 0.2 volt, less than 0.2 volt. So it is again saturation region. So it cannot be in linear region. Okay, so D is not correct, C is not correct, as I said, A is also not correct, so only B is correct. I hope you have understood this problem. Okay, so let me know in the comment section whether this video is really useful to you or not. Okay, if it is useful and if you want to get this kind of videos in future, you can subscribe it, and please press the like button if you have enjoyed this one. Thanks for watching.